ever assembled. The year, 1947. And this is one of the latest transistors, a much more sophisticated device, but based on the same physical principles as its ancestor. The impact of the transistor on the electronic industry and on our society is unquestioned. What is the origin of this remarkable device? The discovery of the transistor is the result of scientific research. Research by men of insight who sought to understand the atomic structure and electrical behavior of semiconductors which had intrigued them for years. For example, electrical conductivity of semiconductors like germanium lies somewhere between that of good conductors like copper and good insulators like rubber. Conductivity of semiconductors increases when their temperature is raised. Conductivity of metals decreases when they are heated. Conductivity of most semiconductors, like germanium, increases when they are exposed to light. And when a metal, like this copper wire, is in contact with a semiconductor, in this case a piece of germanium, conductivity is less in one direction than the other. This characteristic of semiconductors was exploited in the early days of radio to make excellent radio detectors using lead sulfide or silicon. When these semiconductors were touched with a fine wire, called a cat's whisker, they changed the incoming high-frequency signal to a low-frequency signal, which could then be heard with earphones. Later, semiconductors were used to build devices like this copper oxide rectifier for telephone systems. And cat's whisker rectifiers were reactivated during World War II for microwave radar. Even though semiconductors were being used, they were not fully understood. Thus, after the war, Bell Telephone Laboratories intensified the investigation of semiconductors with a hope for understanding. Understanding might bring control, and control was the key to further use. Bell Laboratories scientists decided to study silicon and germanium, which are the simplest semiconductors. The work proceeded in two areas, the studies of bulk properties and surface properties. At a very early stage of the investigation, William Shockley predicted from existing theories of electrical conduction in semiconductors that it should be possible to control the supply of electrons near the surface of a semiconductor by influencing them with an electric field imposed from the outside. If true, this might lead to a new amplifier without the limitations of the electron tube. Shockley devised some experiments to test his hypothesis, but was unable to secure satisfactory results. The negative result of the field effect experiments was an important factor in suggesting to John Bardeen that electrons were trapped in the surface of the semiconductor. This theory suggested new experiments which Walter Brattain carried out. Recently, Dr. Brattain described some of the experiments.
One of the types of measurements that was being done was to measure the contact potential of the surface of germanium. One did this after the fashion of the first experiment on contact potential by Kelvin, by having a semiconductor surface with electrical contact to the semiconductor and placing close to the semiconductor a metal conductor. If one moved the metal conductor with respect to the semiconductor, one in general got current flow in the external circuit. But one found, as Kelvin did, that if one put in a battery of the proper amount, one could move the metal with respect to the semiconductor without getting any current. In studying this effect, we decided at one time to see if we could do this when the whole system was immersed in a liquid. The phenomena that resulted were very interesting, and we finally decided that by using an electrolyte, one should be able to make, in principle, an amplifier out of a semiconductor. One morning, after we had discussed the results of this type of experiment, John Bardeen walked into my office and suggested a geometry for producing an amplifier using the electrolyte.
Bardeen suggested that on a piece of germanium they place a drop of electrolyte, in this case, water. Then to wax a metal wire and push it through the water to make contact with the germanium. The wax would insulate the wire from the water. Another point would make contact with the water. Potentials would be supplied between the water and the germanium, and also between the wax point and the germanium. It was thought that the potential on the electrolyte would influence the flow of current between the wax point and the germanium. This experiment worked. They had produced a semiconductor amplifier. This experiment was the key that led to the invention of the transistor. But there were several problems. The water evaporated too quickly. So they changed the electrolyte to glycol borate, which evaporates very slowly. This worked quite well. But the device would not amplify above 8 cycles per second. They were quite sure that the electrolyte was responsible for the slow response. They tried to replace the electrolyte and its contact with a spot of gold. Instead of the wax point, they placed a wire contact near the edge of the gold spot. It was then they observed an entirely new phenomenon, now called the transistor effect. 4 days later, on December 23rd, 1947, utilizing the transistor effect, the very first transistor was made. This was an eventful day, and Walter Brattain recorded the events.
My notes for the day say this: using the germanium surface, see top of page 197, and the gold contacts, the following circuit was set up. This circuit was actually spoken over, and by switching the device in and out, a distinct gain in speech level could be heard. and seen on the scope presentation with no noticeable change in quality. By measurements at a fixed frequency, it was determined that the power gain was of the order of a factor of 18 or greater. Various people were present and witnessed this test and listened, of whom some were the following: R.B. Gibney, H.R. Moore, J. Bardeen, G.L. Pearson, W. Shockley, H. Fletcher, and R. Bowen. Mr. H.R. Moore assisted in setting up the circuit, and the demonstration occurred on the afternoon of December 23, 1947.
The question in everyone's mind at the time was, could this embryo amplifier be the hoped-for prize, or was it merely an erratic laboratory curiosity? Could it be made into a thoroughly practical device? This challenge was taken up by the Design and Development Group. This new device had to meet extended performance requirements, be reliable, and yet be economically feasible to produce. The point contact transistor was the first production line model. Further understanding and control led to the growing of single crystals of germanium and made possible William Shockley's concept of a junction transistor. This was in 1951. A few years later, the alloy transistor was developed. The industry was now in a period of substantial growth, but more work lay ahead. The frequency of the alloy transistor was definitely limited, and it could only be produced on a one-at-a-time basis. Now came another breakthrough, the diffused base transistor, which is a high-frequency, high-speed device. Working together, the development and manufacturing groups developed today's production methods. Now, a single slice of silicon may contain as many as 2,000 transistors.
The transistor is a truly remarkable device. One of its features is its ability to perform at very low power levels.
As demonstrated here, the light energy from a burning match falling on a solar battery is sufficient to drive this transistor oscillator. A more important feature of the transistor is its reliability, its ability to operate for extended periods of time without changing. It can also transmit and amplify high-frequency signals at very high speed. All these features contribute to modern switching in computer systems. This tiny electronic device is the outcome of scientific research by trained men dedicated to understanding, working in an environment which fosters the uninhibited search for answers to riddles of science which are related to communications needs. For their discovery of the transistor effect, John Bardeen, Walter Brattain, and William Shockley in 1956 shared the highest honor in science, the Nobel Prize.